seed. Then S is U0. Let me make a picture of it. So imagine I have, let's make a picture. So what would be the null space of A? So null space of A is going to be a plane, okay, of vectors. So it's a plane of vectors in which you have a lot of vectors, okay, here and there. So you have all vectors. It also contains the zero vector actually. In the null space of A, there must be zero vector because A multiplied by 0 is equal to 0. Okay, so that. Now I know about what is the relationship between the null space of A and the column space of A star. Column space of A star. I know that the column space of A star is the collection of all those vectors, okay, that are orthogonal to what do you call the null space of A. So this guy represents what do you call this guy represents the column space of A star actually, and this is 0. This is origin actually. Okay, column space is a subspace, so 0 must belong to it. Null space is also subspace, so 0 must belong to it, so it's going to be the common. Now, where are the solutions of these problems? X equal to y. Okay, so this theorem tells you that the solution to this problem lie on a plane actually. They lie on a plane. Let's call this U. So U is what? U is the collection of the solutions of what do you call Ax equal to B. In other words, U contains those vectors which satisfy Ax equal to y. Okay? Since this system is consistent, so there can be lots of solutions actually. There can be lots of solutions. Are you getting the point? By the way, this U0 is not only solution of this, but this U0 is also solution of Ax equal to y if you take this to be your, if you take this to be your x actually. Okay? So one such x is really, this A star U0. So U0 is also going to be sitting in this plane actually. So the U0 vector is also going to be sitting in this U0. I guess U0 is also going to be there actually. So in this U0 vector. Anyway, this is what. Now you can see that if this is a plane and the column space is the axis, then the column space is going to hit this plane of the solutions of Ax equal to y at a unique point actually. They both intersect at one single point. And this point of this vector is really something that is in common is your S actually. So S is the minimum norm solution actually. So S is that vector that lies on what do you call? You may interpret this plane as that in which each point is a vector. Okay. Then this point is representing the vector that lies on the column space of A star. And it also lies on what do you call the space of the solutions of Ax equal to y. So therefore, this S is going to be the only solution that solves that is common with what do you call the space of the solutions of Ax equal to y. So S is the only solution. So it's a unique solution first of all, a unique point, a vector that solves say Ax equal to y, and it lives on the column space, but it is the only solution of what do you call So the B part is like that. Okay, F is the only element in the column space that solves, what do you call this system? That solves, what do you call this system actually. So I hope that this makes sense to you. This makes sense to you a little bit actually. Okay. Okay. So I hope this picture is making sense to you. So this is null space of A. This axis is representing the axis of vectors that are orthogonal to the null space of A, and U is the set of the solutions. Okay, that is really, what do you call, the set of the solution that solves Ax equal to y. Another thing that you can see about U is that U is a translated version. So these two, planes are parallel to each other. So if you translate the null space by some unit, you're gonna get the space of all solutions, okay, that solves Ax equal to y. Okay, that solves Ax equal to y. So if you take this plane and translate a bit, then this is going to be the solution of all. This is going to be the collection of all vectors that solves Ax equal to y. And among those solutions, S is the only vector that not only lives on this plane, in other words, it solves Ax equal to y, but it also lives on the column space actually. So you can say that this is a pictorial representation of what you have here. So even this picture is an abstract picture actually. So let's prove it. Let's prove it. So here's a proof. Here's a proof of it. Here's a proof of it. We know from our abstract result, maybe I should mention it here. We know from our abstract result, we proved it last time, that if U is a subspace of the inner product space V, then the V, this inner product space V, can be written as, what do you call, direct sum of U, okay, U, and orthogonal perp of U. Orthogonal perp of U. If U is a subspace of, what do you call, vector space. So this is, then U will be the direct sum of V, U and U perp. In other words, every element in V can be uniquely written as an element from U and an element from U perp actually. Now what I want, okay, in our case, take V to be Fn, okay, and U to be, what do you call, the null space of A, okay, it's a subspace. Then I know that Fn can be written as null space of A, direct sum, the orthogonal perp of the null space of A. Okay, this is what it is going to be. Now, okay, so I think we should not take U as the null space, but we take U as the column space of A star. This is what I mean. Then Fn can be written as the column space of A star, direct sum with the column space perp of the column space of A star. But we just saw, a moment ago, okay, that the orthogonal perp of the column space of A star is really the null space of A star. Okay, this is what that you're gonna get. Now, what does this shows? That every vector in Fn can be written as an element from column space of S star and element from the null space of A actually. Okay, null space of A. Now let's take a solution to this task. Since this is a consistent, system, so there must be a solution. So let x naught be a solution. X naught be a solution. X naught from Fn is a solution star. That is Ax naught equal to y. Okay, this is what. Now, since x naught is an element in is a vector in Fn, so it can be written as a sum of a vector from the column space of A star. It can be written as an element from a vector from column space of A star and a vector from column space of null space of V actually. Okay, so the x naught can be written as a sum of, say, S is an element from column space of A star and V, where S is an element from column space of A star and it's unique actually, and V is an element from the null space of A. In other words, so if I show this, that this x naught, imagine this x naught is like a unit vector actually, so it's a vector. Okay, so x naught is going to be a vector in U because it's the collection of the all vectors that solves the system star actually. Then this x star can be written as a sum, as a vector S from the column space of A and a vector from the null space of A. So let's say that this is a vector V, okay, which is a vector which is really a vector in the null space of A, and S, say, is the vector, okay, that lives on the column space of A actually. So then this can be written as the sum of these two vectors actually. So if this is V and this is S, then this is S as well. So the x naught can be written as V plus this vector, or V plus this vector actually. Okay. So I can also put them on this place. Now, if I take my A and operate it on x naught, I take my A and operate it on x naught. So that means that A is really S plus V, but this would be equal to AS plus AV, okay, and AX naught is really Y. Now V is from the null space of A, so the AV is going to be equal to 0. So this would be equal to AS. Okay, this would be equal to AS. So what does this shows? What does this show? That if you have any solution x naught of the system star, this solution can be written as an element from the column space and element from null space, and that element from the column space, okay, x naught is the sum of S plus V, that element S from the column space is also solution of the star actually, of the star. Okay, so this shows that the star has a solution S that lives in the column space of A, that lives in the column space of A. But in order to prove this, you need to still show two things actually. Number one, that it must be unique. Number two, it must be minimum norm actually. because the claim is not to find the solution in the column space of A, but the claim is to find the solution that is unique and minimum norm actually. Okay, so what we did, what we showed, that there is a solution S in the column space of A star which solves Ax equal to 1. Ax equal to 1. Now, say, let me get rid of this picture. I hope you have made this picture. Thus you can say, thus we can say, hence we can say that every solution x of a star is of form x equal to s plus v, where x belongs to v and S belongs to the column space of A star, and AS is equal to Y. Actually, it solves the A. Okay? That it solves the star as well. Now I want to show that this S that lives in the column star of A star, has a smaller solution than has a smaller norm than the norm of x actually. Because if x is an arbitrary solution of this, then x can be written as s plus v, where s is the element from the column space of A star, okay, and v is some vector, not from v but the null space of A. V belongs to the null of A, and S is in the column space of A star, and A is equal to Y. Okay? And if I compute now, say, the norm of x, okay, norm of x. The norm of x, or maybe square of it would be equal to s plus v square actually. It would be equal to s plus v square. What do I know about s and v? That s is from the column space of A star and v is from the null space of A star, so they must be orthogonal to each other. So s must be orthogonal to each other. So if s and v are orthogonal to each other, then by the Pythagorean theorem I can say that this is equal to s square plus norm of v square actually. Okay? By the way, this norm is really the 2 norm, because you are talking about Fn space. And if this is the case, then what does this show? So if I drop this term out of this term, so this would be, you can say that bigger than or equal to norm square of S2. Norm square of S2 actually. So what does this show? That the solution of star x equal to y, okay, that lives in the column space of A star has norm less than or equal to, okay, that is the norm of S is less than or equal to the norm of x actually for all x that solves Ax equal to 1. So you're going to say hence this S belongs to what do you call the column space of A star is a minimum norm solution. Minimum norm, what do you call solution? Okay. So the solution that lives in the column space of A star is the minimum norm solution, because its norm is going to be bigger than or equal, less than or equal to the norm of any solution that solves a star actually. But there is also a claim that it must be unique actually. In other words, this S that solves AS equal to Y and lives in the column space of A star, and this S that solves AS equal to Y and lives in the column space of S star, they can't be different. So you can't have more than two elements in column space of A star that satisfies what do you call this actually. So let's think about the uniqueness of it actually. Uniqueness of it. So why the solution, the minimum norm solution is unique actually. Okay. Why the minimum norm solution is unique? So suppose S prime belongs to Fn is another minimum norm solution of what do you call star. Okay. Now since this S prime is also in Fn, so it can be written as S prime equal to S plus some vector V, where the S is from the column space of A star that solves what do you call that solves AX equal to Y, the solution is star, and is the minimum norm solution. So it's the minimum norm solution that solves star. And we are claiming that S prime, there is another S prime in Fn that has a minimum that has a minimum norm solution. Okay, but since this S prime is in Fn, so you can write it in this manner. But here is the key thing. So if we take, for example, the norm of S prime, okay, this should be equal to. By the way, since the norm of S prime and the norm of S are the minimum actually. So they must be, what do you call, the same. Their magnitude must be same actually. You can't have that, okay, I have a S prime has norm, what do you call, 1 and S has norm 2 actually. So we're going to say, this is not minimum norm. S prime is the minimum norm because it has a minimum. But if I'm saying that there are two vectors which are different from each other apparently, and they are the minimum norm solution of a star, then their magnitudes must be equal actually. Their magnitudes must be equal. And if their magnitudes are equal, okay, or maybe write S here and S prime here, then this means, or maybe I put S square and again use Pythagorean theorem, S plus V square. Then by Pythagorean theorem, this will be less than or equal to norm of S square plus, or exactly equal to norm of S square plus the norm of what do you call V square. Okay, and this shows that the norm of S square is equal to norm of S square plus the norm of V square. This implies the norm of V square, V is equal to 0. This implies V equal to 0. And if the V equal to 0, this shows that S prime is equal to S prime. So what does this show? For this system, you can't have two minimum norm solutions actually. Okay? So first we proved there is a solution, and every solution can be written as S plus V, where S is a minimum norm solution, and this solution must be unique. And that minimum norm solution lives in the column space of A star. Okay? Column space of A star. Now let's get to the what you call B part, which says that S is the only vector in the column space of A star. We saw it pictorially that you can't have more than one vectors, okay, that lives in the column space of A star and solves what do you call this problem, Ax equal to y. Okay. So in B part, we will like to show that S is the only solution of A star, okay, of problem, what do you call, a star that lies in the column space of A star. So suppose there are two actually. Suppose there is S and S prime in the column space of what do you call A star, such that they solve the star actually. In other words, AS is Y and AS prime is also Y. Okay, so they both solve the system actually. Now, here is something interesting actually. Here is something interesting. By the way, if I subtract these two equations, what does this shows? That AS minus AS prime would be Y minus Y equal to 0. So therefore A times S minus S prime must also be 0. So this means that S minus S prime must belong to the null space of A. Null space of A. Okay? Moreover, we also know that the column space is a subspace of Fn. So it's a subspace as well. Column space is, because it's a span actually. It's simply span of the columns of A, columns of A star. Okay, so it's a span. The span is always a subspace. So it's a subspace. If it is a subspace, then S minus S prime also belongs to the column space actually. Now, since column space of A star is a subspace of Fn, so S minus S prime will also belong to the column space of A star. So this means that S minus S prime belong to the column space of A star, and it also belongs to the null of A. So can you tell me that what could be this vector actually? We saw it pictorially, that if this is column space and this is really, what do you call, null space, then what could be the vector that is common in both actually? So the only vector that can be common in both is 0. Okay, it's 0 actually. Or we also know that since Fn, okay, Fn is a direct sum of the column space of A star, okay, and null space of A. So in these two subspaces, there can be only one vector that is common, that is 0 actually. So there is only 0 common in both. So that means that if S minus S prime belongs to this intersection, then S minus S prime must be 0. This implies that S must be equal to S prime. And what does this shows? What does B adds into the information? It shows that there is only one vector in the column space of A star that solves Ax equal to Y. You can't have more than one vector in the column space of A star actually. Okay. Now let's move to the part C of it actually. Let's move to the part C of it. Part C. So the part C says this system is consistent, okay, and any solution that solves this system, if you multiply that solution with A star, you're going to get the minimum norm solution actually. Okay. So how to do it? It's very simple. So here's an interesting thing. Now so by part A and B, we know that there is a unique solution of this system, that lives in the column space of A star, and there is no other solution in the column space of A star that solves this. So since S belongs to the column space of A star, and since S belongs to column space of A star and solves AS equal to what do you call Y, okay? So this